Okay, so good evening once again. Welcome to this series of lectures which have been organized by India-based Neutrino Observatory, which is in fact titled as All About Neutrinos, online interactive lecture series for general audience. Today we again have Professor C.S.Unnikrishnan from Tata Institute, Mumbai. I say again because he did, if you recall, he did give a talk very early on in this series, end of May, and he talked then about the spin in the difference between bosons and fermions. Okay, so and today again he's here to talk on another very interesting topic, the puzzles of quantum superposition and the intrigue of the particle and a wave. For those of you who, it's very unlikely, but if you don't know who is Professor Unnikrishnan, he is a professor of physics at the Tata Institute of Fundamental Research, Mumbai. His research interests are experimental as well as theoretical aspects of fundamental issues in gravity and quantum physics. He has set up a laser cooling laboratory in TIFR long ago, where the first Bose-Einstein condensate in India was actually produced. The major theoretical contributions of him are in the theory of cosmic relativity based on the gravity of matter in the universe, and a universal action mechanics solving the widely debated fundamental problems of quantum mechanics. Unnikrishnan is a proposer scientist of the now all well-known LIGO India project and a member of the LIGO scientific collaboration, as you know, which detected the gravitational waves. Unni is also known for many of us for his interest not only in physics, the fundamental physics, but also his interest outside physics research as well, mainly on music and films, and more especially, their structure and the process of their creation and so on. So this is a brief words about today's speaker, and now over to Unni for his interesting lecture, which is titled as The Puzzles of Quantum Superposition and the Intrigue of Particle and a Wave. Over to Unni.
Thanks, Satya. It's my pleasure to come back to this forum to give a talk. It's also for my own benefit, for gaining clarity. Today, I want to talk about what is known as superposition of states in quantum mechanics. Of course, it is relevant for neutrinos, but it is relevant in the larger context. The concept has challenged every physicist for the last 1 century or so. And the problems faced by the pioneers are not yet solved. That is why this topic is very important. And I will try to convey certain peculiarities of the consequences of quantum superposition. Now, there's a fundamental question when you talk about quantum mechanics. Can a solid particle can also be an ethereal wave? If it is, then a stone can be both heavy and light. The question is, can a piece of matter be here and there? Because that is the way people express these things in common language. Some believe that such matter exists, which can be here as well as there. And some believe that it doesn't. The superposition of the wave functions of the Schrodinger equation, representing discernibly different physical states, is at the core of peculiarities of quantum mechanics. But the physical reality behind the peculiarities of quantum mechanics, what it really represents as a physical entity, has remained a mirage for nearly a century from the beginning of quantum mechanics. In this talk, I will clear the view and reveal the physical reality behind the wave-particle dual entity in dynamics. I How do I make it go? Okay. I wanted to see the top of this.
You may have to bring back, yeah. Is there something more?
No, just the title thing. It's blocked by some band of. It is not going away. That.
Okay. Do you want to break this PPT for a while?
It's okay. I'll manage. Yeah. Now, physics uses several unobservable, what is called unobservable, something which cannot be. It is stuck. The screen is stuck. I'll stop and re-share. Okay. Now, physics uses several unobservable quantities like fields, electric, magnetic, and gravitational fields. Of course, from school days, one is familiar with showing magnetic fields with iron filings and so on. But nobody has released in a magnetic field or electric field or gravitational field. All one sees is matter and their interactions. And we call these interactions as mediated by fields, which are our imagination, which is a consistent imagination. I've written extensively about unobservable quantities in physics elsewhere. That is not the topic of this talk. I just want to give some references here. Now, even space and time, they are the supreme unobservable quantities in physics. As you know, you cannot see space or time. You can only see distance between material particles and time measured by a material clock. Now, when you come to wave function, you don't even know what that object is. It's unobservable, of course, but you cannot even relate it to something familiar in physics yet. Some people think that it's a matter wave, which de Broglie sort of speculated on. Now, there are two phases of matter which is familiar to us. One is particles, other is waves of something. When we say waves, we always mean waves of something, like waves on water, waves of sound, waves of light, and all that. Now, one peculiar property of waves is that they can superpose and interfere, which is seen in any kind of wave, even for water waves, sound waves, or light here. They show similar property of superposition and interference, where they can cancel each other. So the property of superposition is that if there are two waves, they can, of course, add. They can also cancel each other and become nothing, which is very important, which particles cannot do. And the representation of this property, the wave and its ability to superpose, can be represented nicely mathematically using vectors. So there you see that you have a vector which can be resolved into its component states, which means this vector S is represented as a linear superposition of these vectors X and Y with some coefficients. Now, when we say waves, superposition, and so on in quantum mechanics, what we really mean is only this much. That is, quantities which can be added together, which can cancel each other, and so on. That needs a mathematical representation. So we know how to deal with the superposition mathematically, and we do not need to know or understand what exactly is superposing physically. So these are two separate issues. The two together are needed when you make a physical theory. Now, there is a familiar example which all of us talk about when we talk about quantum mechanics and superposition. If you have a source of electrons, which you know are discrete countable particles, the source emits these electrons, it comes to a screen which has two slits, and then there is a screen. Now it is very well known that if you look at the screen and you have some suitable detector of these electrons here, what you see is just spots, this kind of spots, one by one. But if there are this, which is very similar to what you see on a television screen, CRT screen. However, if there are these two slits in the path of these electrons, and the electrons have well-defined energies, then after some time, after some accumulation of the number of electrons, it shows a pattern which looks like exactly like the pattern which we saw earlier with light interference. However, the detection, the particles are always seen only as particles, discrete quanta. And if you look at these particles near the slits, it's either in one slit or in the other slit. It's never in both slits. But it is true that this kind of a pattern forms after accumulation of large number of electrons. In fact, Feynman called this the only mystery in quantum mechanics. How can these particles, which will only pass through one of those two slits, form interference pattern which needs something passing through both slits? This is the only mystery in quantum mechanics. Now, if you look at optics, classical optics, one is familiar with, let's say, circularly polarized light, which I represent like this. Such a beam falling on a birefringent crystals splits into two beams, and you can call it vertical polarization and horizontal polarization. This happens, it is very familiar to everybody. Now, the left circularly polarized light can be represented as a superposition of vertical and horizontal polarization with some coefficients, which I am not writing here. Similarly, using the same two states, vertical and horizontal, one can also represent the right circularly polarized light, which is a different superposition. These are two orthogonal superposition, orthogonal polarizations. This is familiar in classical optics, of course, has been known for almost 200 years. However, if the same experiment is done with light, but with a highly attenuated source or a single photon, an atom emitting light, or any of the modern sources of single photons emitting here, then what is seen after the crystal is either this or that, not both. Either the photon comes out as vertical polarized or it comes out as horizontally polarized, exactly like what we saw in the case of electrons. It is a representation of the physical state of a particle that superpose and not the particle itself. Because if the particle was superposing, each particle should come out in both paths. That doesn't happen. So something else is superposing. The need for superposition in quantum mechanics There are several justifications one can give it. Of course, purely formally, quantum mechanics is described by what's called a Schrodinger equation, a first-order partial differential equation, linear equation. Therefore, if psi1 and psi2 are two functions that satisfy the equation, so is the linear combination A psi1 plus B psi2. So that way, formally, linear superposition is valid in quantum mechanics. But of course, one can talk about a physical reason for the need of superposition. If you look at de Broglie's proposal of particles behaving as waves, there must be a matter wave, matter behaving as waves. In fact, that's how Schrodinger started on this problem. Usually, electron diffraction from crystals or interference of electrons and neutrons, etc., at two paths is considered as a direct proof of matter waves. Many people consider that. And Schrodinger wrote an equation for the dynamics of the time evolution of the matter wave. However, if you look at the history of this problem, what Schrodinger wrote was actually the standard wave equation in the beginning. What you would write for sound, light, and so on. This is a standard wave equation, second order wave equation. This is exactly what Schrodinger actually wrote. Then through a series of manipulations, after several papers and reasons, he derived what is called today as a Schrodinger equation. They are the same equation actually, putting in certain assumptions. So this is a non-relativistic equation for the dynamics of microscopic particles today, very successful theory. Now, there are several foundational physical problems which arise because of this implications of this equation. Of course, there is something which was discovered much later after Schrodinger wrote this equation was what is called indeterminism. It came through another route from the discovery of same theory by Heisenberg. But anyway, let's not go into details there. The point is, if you prepare a quantum system in a particular state, yes, prepare it every time in the same state, and then do an observation for some physical quantity. It could be position, it could be spin, direction, many of those properties, some physical property, which can have many possibilities. What you see is, though the prepared state is exactly the same, the measured state, the observed state can be different, appearing randomly. So therefore, this kind of a situation needs superposition to describe it. In the sense, the same state, yes, is also written as a superposition of three different states here, A, B, and this should be C, with some coefficients. And when you have this kind of a system, then you need one more input to describe what is this measurement, what is happening during this measurement. This is exactly the same situation as I said earlier. You have a circularly polarized light and a measurement situation. You see either that or this randomly with some probability. So there, what came in help was what is called Max Born's rule of statistics in quantum mechanics, where the square, absolute square of this wave function in Schrodinger equation, psi square, psi star, is equal to the probability density which is involved in the case of this discrete states, this coefficients, the square of those complex numbers will be the probability for getting each of those states. So you have the same state prepared every time, but the states A, B, and C are obtained with probability A square, B square, and C square. So these are the fundamental rules of quantum mechanics. Now we ask, what exactly is superposing in quantum mechanics? If the wave property belongs to the particle, it should be the particle itself. It should be capable of superposing, but it is not. Is it any of the physical property of the particle, like energy, momentum, etc.? No, definitely not. What all we can say is it is a wave function which is superposing, but we have no idea what that corresponds to physically. In fact, from Feynman lectures, he says historically the electron, for example, was thought to be like a particle, and then it was found that in many respects it behaves like a wave. So it really behaves like neither. Now we have given up. We say it is like neither. There is one lucky break, however, electrons behave just like light. The quantum behavior of atomic objects is the same for all. They're all particle waves, or whatever you want to call them, because one doesn't understand what they are. So what we learn from the properties of electrons will apply also to all particles, including photons of light. So we are operating on the strength of the same kind of behavior for all particles, so that we can have a common theory. So we call the specification of the physical system state in quantum mechanics as just a psi function, as preferred by people like Einstein and Schrodinger. They never called it the wave function. Now there are some birth defects because of superposition in quantum mechanics. One is called wave function collapse, which is also maybe familiar to you. You start with a particle which you prepare, like electron, then send it through a system which can have different possibilities. It could be part of an interferometer. Then try to see where the particle is. Observations. You will either see here or there. The particle will be observed here or here, and never in both states. And the probability for observing the particle here or here is given by this psi1 star or psi2 star. But once observed somewhere, the probability is 1 where it is observed, because the particle is already there. Then everywhere else, the wave function should collapse to 0, because there cannot be any probability to be anywhere else once it is observed in one place. Therefore, probability is 1. It cannot be anywhere else. Therefore, as soon as this observation is made, the wave function should collapse to 0 everywhere else. As long as Bond's rule is part of quantum mechanics, this cannot be avoided. So this is already a problem, because if psi is something physical in space and time, one doesn't like things disappearing somewhere else suddenly because of some observation mass made locally here, right? And there's a famous example of Einstein's, some source of particles with a narrow aperture here. Then the wave function, if you calculate in quantum mechanics, it's a spread out, almost like a plane wave. And there is equal probability for detecting this particle somewhere on the screen. All that is fine. Within the mathematics, that is fine. Now, suppose a particle was detected here on the screen. Then, of course, as we said, the wave function should collapse to 0 everywhere else. But there is a more serious problem. There is no rational conclusion of the past. That is, suppose I ask the question, I detected this particle here now. I ask the question, where was this particle just a nanosecond earlier? Suppose I ask that question. I would like an answer in which I would have liked if the answer was something like, okay, the particle was nearby, maybe within a few centimeters around this position where I detected it. No, you cannot. Quantum mechanics says you cannot say such things in quantum mechanics. The particle was supposed to be everywhere. The wave function was supposed to be everywhere. you cannot say that the particle, just because it is detected here, it was near this detection point 1 nanosecond or 1 picosecond away. It's a serious problem because you cannot just extrapolate back to past. So that's why Einstein in 1949, well after all this was understood, he said the following: all my attempts to adapt the theoretical foundation of physics to this new type of knowledge failed completely. It was as if the ground has been pulled out from under one, with no firm foundation to be seen anywhere upon which one could have built. Several years later, Feynman famously said, I think I can safely say that nobody understands quantum mechanics. Very recently, Steven Weinberg, who was not somebody who was very bothered about foundations of quantum mechanics earlier, says, even so, I'm not as sure as I once was about the future of quantum mechanics. It's a bad sign that those physicists today who are most comfortable with quantum mechanics do not agree with one another about what it all means. Now, we saw this example of superposition of light, states of light polarization. If you have a 45-degree polarization, we can express it as equal superposition of horizontal and vertical. And both polarizations can be expressed as this superposition with the different signs between horizontal and vertical. Similarly, the vertical and horizontal can be expressed as linear superpositions of this 45-degree polarization. It's reciprocal. Also with the same state, horizontal and vertical, the same, just as two state, we can also represent the circular polarization, right circular and left circular. And then we need, of course, once you have finished plus and minus, we need something else to do that. That is why the complex numbers would be required to do that. The point is, with just two states, H and V, all other states, infinite number of them, are represented. Of course, in this example, the physical states are of the same kind, angular momentum. So I want to show, especially for the benefit of people, students who might be listening, another example where you have one particle, there are two observable properties, and with two values each. So here also it's all two valued, like plus and minus, right circular, left circular, and so on, but two observable properties instead of one observable property. Let's take a particle which can be big or small, or more massive or less massive. So that is a two-state system, single particle. So the general state of the size, property size, will be a linear superposition of big and small. That's okay. Now there is another property, physical property of the same particle. Let's say color. It can be red or green. Again, two states. There can be a general color state, which is a superposition of red and green. Now the point is that if you use two of this state, big and small, there are cases where the red and green can be expressed in terms of big and small. There's an overlap between the color state and the size state, which sounds strange, but that's how things go in quantum mechanics. For example, let's start with the big state. There's a single particle in the state big. As we know, the big state is a superposition of red and green, because red and green is the base state, the fundamental state we want to express everything in terms of these two states. So it should be a superposition, and here I have chosen equal superposition of red and green, and I call it big. If this is the case, of course, the state small also can be represented in terms of red and green, just as we expressed linear superposition as well as circular polarization, everything in terms of this just two states, vertical and horizontal. So big state is represented by red and green. Small state also can be represented in terms of another superposition of red and green. Now let's start with this. Let's say we start with this big state. It's a superposition of red and green. Then ask the question, what is the color state of the size state B? So we start with size state, which is big, and then ask the question, what is the property, color property of this big state? Now, since the big state is an equal superposition of red and green, if you observe for color, you will get either red or green with equal probability. Suppose we got green in a single measurement. It's a single particle, single measurement, started with big, measured for color and got green. So this is a situation. We started with pure big, asked the question, what is its color state? And we got green. If we ask the same question again, what is its color again? What's the color state of what we got? You will get exactly the same answer again. That's all you can get. However, now take this green state and ask the question, what is its size state? We started with big, then we measured for color, we got green, then we are again asking what is its size. Now in quantum mechanics, we cannot conclude. Since we started with big, it should be big because the color states are superposition of the big and size state, big and small state. If big and small are linear superposition of red and green, then red and green are linear superpositions of big and small. Therefore, after measuring green, if you ask again the question, what is its size state, you can get either big or small with equal probability. You may get big, you may get small. Now, again, if you ask the color, question of color, you get another random result, red or green. So this is what is called quantum indeterminism. Of course, people are very puzzled when I give this example. People have no problem when they hear the example of polarizations or spin, because it's the same kind of quantity. Here we are talking about two different properties, color and mass, or color and size. And they can be this interchanging indeterministic results when we do answer separate questions. And I want to give a concrete example, which is the topic of this seminar series, which is neutrino. For example, neutrino comes in two flavors, right? Or three flavors. Let's take two here. And they are linear superpositions of what's called mass eigenstate, mass state. So it's like size, what I talked about. So neutrino, the color states are written in terms of some size state here. The flavor states are written in terms of the mass states. This also means that the mass states are, of course, linear superpositions of the flavor states, always. So though we don't deal with this normally in experiments, we deal with this, but this is the fact. So if you continue with neutrino, of course, we know it's a charge zero, mass nearly zero particle with very peculiar properties, which we write as a linear superposition. Each state, physical state of a neutrino is written in terms of the mass states here. I take two for example. Now, the consequence of writing like this is a new consequence because mass states are involved. In the earlier example, which I talked about color and size and so on, this kind of a consequence do not come because here mass has a specific physical meaning in the theory of physics and in the physical world. Mass is equal to energy, and it is very important fundamental quantity in time evolutions. So the consequence of neutrino flavor state being superpositions of the mass state is a consequence is what is called neutrino oscillations, which everybody is familiar with. But then when you ask a question, what is oscillating? We talk very freely about neutrino oscillations. Now the question is, what is oscillating? There is no real answer. If we have a superposition of this form, mass state, one mass and another mass, which are different, of course, the mass is associated with what a frequency in particle physics and fundamental physics, as you know, which is what is called Compton frequency and so on. So if you have superposition of two mass states in a single particle, one would expect that there are two frequencies associated with that particle somehow. If there are two frequencies are associated, then the sum of those has to oscillate in a particular way. For example, two sinusoidal functions with slightly different frequency will have a some frequency and a different frequency modulating it. And another superposition with a minus sign will have a different behavior, which I will show here. If you have a particular superposition of these two frequencies, then some phenomenon like beats will happen, of course. But the other superposition, which was if you look at the corresponding square of the wave functions, square of the quantum state, the modulation, the slow modulation looks like turn out to be the probability. So here, if you call the electron neutrino as a sum superposition, this is a probability of seeing this neutrino as an electron as a function of time, which is oscillating. The other superposition, which is a minus with a minus, will have a different, it is very similar looking, but it's phase shifted. Therefore, its probability will be oscillating like this. The sum of these probabilities is always 1. The particle is either an electron neutrino or a muon neutrino. There is nothing in between there. Now, we can ask, so we know that there are oscillating functions in this problem. However, and we also know that when the probability is 1 here then it's definitely an electron neutrino. When there is probability 1 here, it is definitely a muon neutrino. And there is an electron neutrino. The question is, what is it in between? What is it in between? If a single particle, if this represents a single particle, then one would have expected something in between, which is oscillating exactly like this probability curve here. No, that is not the physical truth is the neutrino can be either electron type or muon type. There is nothing in between. There is no neutrino which is a combination of electron neutrino and a muon neutrino, a single neutrino. It is never seen. Therefore, this picture will not work. There is something else happening physically. We know that we calculate probability and so on, it oscillates like this. But neutrino is not oscillating. Neutrinos can also oscillate. Let me say it slightly more strongly. Suppose you have neutrinos coming from some source, passing by. If we could see the flavor change, it will change the flavor from electron neutrino to muon neutrino at some particular point, suddenly, randomly. There is no smooth transition from an electron neutrino to a muon neutrino to electron neutrino. If there is any such imagination, it is wrong, because single electron neutrino, this is what will happen. It will change a muon neutrino and goes. Another electron neutrino, same preparation, it will happen at some different time. Now, it randomly. It may also happen that it never happened while you are observing. Electron neutrino comes and goes as electron neutrino. So different electron neutrinos at different, though it started with the same initial conditions, its conversion to muon neutrino happens at random times. Each neutrino changes to another neutrino flavor at one point in space and time, randomly, suddenly. There is no smooth oscillation in neutrinos. This proves that single neutrino is not a superposition of three waves corresponding to three different masses. It proves, because this is what you see. Because if it were, the flavor change would have been smooth. The true physics is something else. This is easily understandable if we look at another very laboratory kind of an example. Neutrino is complicated because we cannot see the whole transition from electron type to muon type. No, I can only draw it schematically using the knowledge I have from atomic physics, for example. This is a three-level system which I have shown here, 1, 2, and 3. And there is a strong transition here, which I can excite with a laser. So when I do this, I see strong fluorescence from such atoms in this blue. But because it has its third level, which is a long-lived, slightly metastable level, once in a while the atom, the photon can be emitted into this state. So the atom can end up in this state 3 once in a while. There's a good probability for that as well. If it happens, and since it is long-lived, this fluorescence will stop till the atom again comes back down to the ground state, because that is where the laser is. If it comes back here, again fluorescence will start. So this kind of a system, if we use in the laboratory and do this experiment, this is a result from the barium ion. So the specific wavelengths are for barium ion. You can see there is a strong fluorescence which happens, and suddenly it stops. This means the atom has come here, single atom. It has come here. Until it comes to the ground state again, the fluorescence stops. Once it comes, again it jumps here, and fluorescence continues. Again, when it goes to 3, it stops. So quantum mechanical changes happen only as quantum jumps. It's never smooth. But if you have a lot of these ions on which you are measuring the probability, there will be a smooth transition from this state to that state and this state and so on. Almost like what you saw on the sinusoidal oscillations there. So single systems are never in superposition in the usual sense of the word. Mathematically, it is true, that's the only way quantum mechanics are able to represent it. But single systems always change state by quantum jumps, whether it is an atom or a neutrino. So neutrino doesn't oscillate, neutrino jumps from electron type to muon type to electron type and so on. And yet we have only the kind of representation using superposition and so on for describing the theory. That's why Schrodinger in despair said, if we are still going to have to put up with these damn quantum jumps, I'm sorry that I ever had anything to do with quantum theory. When he was discussing with Bohr, that's what he said. Now I want to show you another bizarre situation coming from superposition. Suppose you have two systems, not one system, two systems which interact and then they separate. So that is the situation. Two systems, they interact and separate. Now there are two state systems, one property, two states. For let's say we take color here. But because of the interaction, suppose there is a constraint, a correlation. That is, if one is green, the other is red. And if the first is red, the other is green. You can never have both red and both green. Suppose that is a physical constraint because of the interaction. This happens in many situations. Now again, in quantum mechanics, we will represent this system using superposition. That's the only tool we have. So the interaction, separation, and you have only one first green, then the second is red, or the first red, second is green. There is no red, red, and green, green. So it's a simpler superposition, right? It is just this with equal probability. See, seemingly a simpler superposition. Now, it's very strange if you ask the following question. What is the quantum mechanical physical state of the particle 1 or 2? So I take this particle, they are separated. I have not observed, I want to observe. But before observation, I am asking the question, what do you think is the quantum mechanical state of the particle 1? I can look at the superposition because this is a quantum mechanical description of this particle. This is the only thing we have in theory. Now the problem is, if you look at the superposition, it is not G, it is not R, and it's not a superposition of G and R. Because if it was a superposition of G and R, I could have taken out that superposition, factored out, and I would have had a different state. I cannot take it out, a superposition of G and R. So it is not G, it is not G, it is not R, it is not G, a superposition of G and R. But these are the only possibilities available in the theory of quantum mechanics to describe the system. So you see, the answer to the question is particle 1 has no physical state whatsoever. It doesn't have any physical state in the theory of quantum mechanics. It's called entanglement. This kind of a state is called entanglement. It looked like a simpler superposition because instead of the 4 general terms, we had only 2 terms. But the consequence of this kind of a superposition is that this particle doesn't have any physical state in quantum mechanics. This particle doesn't have any quantum mechanical state. The two together has a quantum mechanical state, which is this. So you see, the entangled state, it has a very terrible meaning. If you ask this question, what's the state of each particle? The answer it is there's no physical state. Because most general state of the system is a two-state system. One, first particle, either plus or minus. Second particle also plus or minus, red and green, plus or minus. Then the joint state, the most general joint state is just this, the product of these two. Both can be plus, both can be minus, one plus, second minus, one minus, second plus. So that is a general state in quantum mechanics. But the state what we wrote down was this state, which is only these two terms. In the most general, if each of them had states, S1 and S2, this is a general state where these coefficients should obey a certain relation. The squares of all these coefficients should add up to 1 because they are probabilities. Then there is a particular relation. The product of R and S should be equal to product of P and Q. But it's not valid here. P and Q are non-zero, but R and S are 0. So this is violated. So you see, neither system has any physical state because S1 2 cannot be written as S1 product S2, which is separate state for S1 and S2, separate states for first particle and separate second particle. Now we can ask, this is why Schrodinger was very worried about quantum mechanics. If you take, for example, an atom, which is a microscopic system, and a macroscopic system like an insect, the atom can have ground state and excited state. Let's call it 0 and 1. The insect can also have two different quantum states, the live insect and a dead insect. Now I put them together into a box and close the box. They will interact. And the interaction can be such that if the atom remains in the excited state, nothing happens to the insect. But if the atom de-excites, it kills the insects. Then these are the only two possibilities. Therefore, the joint state of such a system becomes atom in the excited state, cockroach live, atom de-excited, ground state, cockroach dead. The other two possibilities are not there. But once you have that, I can ask the question, what is the physical state of the insect? At any time, I can ask this question. And this is a quantum mechanical description of the evolution of these two systems together. And every answer should come from this state. And that state says insect has no state. Though we know that it is inside the box. Insect has no state in the theory of quantum mechanics. It is not live, it is not dead, it is not in a superposition of these states. Many people make a mistake of talking about Schrodinger cat and so on, that it is in a superposition of dead and live. It's a wrong thing to say. It is not live, it is not dead, it is not in a superposition of these two states. It has no physical state in quantum mechanics. And this is where what is called the quantum measurement problem comes, which is supposed to be the most important open, unsolved problem in fundamental physics today. Because instead of the insect, if I have an instrument, a measuring instrument interacting with a microscopic system to observe an state of the atom, state of the neutrino. So this could be a neutrino detector and this could be a neutrino interacting with each other, Neutrino is either detected or not detected. It has an entangled state. The entangled state between the state of the neutrino and the state of the apparatus, state of the atom and the state of the apparatus. There are only two possibilities. It's always an entangled state. You can ask the question, what is the state of the apparatus after the interaction? It has no state, because in quantum mechanics. But we observe atoms, we observe neutrinos. Therefore, something is wrong with the theory of quantum mechanics. We are able to observe. But quantum mechanics, if it is a universal theory applicable to both atom and the apparatus, then it should not have happened, because we can never reduce the state. Because if you have this interaction, this is the only possible state. Now, if you bring in a third observer to observe the apparatus, quantum mechanics applies to that observer as well. It becomes an entangled state containing three different systems. It's an infinite regress. So therefore, there are only two possibilities. Either quantum mechanics is not correct, or quantum mechanics is not applicable to everything in this world. It's only applicable to microscopic particles, not to macroscopic system, which means there is classical mechanics and quantum mechanics has two separate theories. So you can see all these problems. That's why Weinberg recently said, the problems of understanding measurement in the present form of quantum mechanics may be warning us that the theory needs modification. Unfortunately, these ideas about modification of quantum mechanics are not only speculative, but also vague. And we have no idea how big we should expect the corrections of quantum mechanics to be. I'll just skip this. This is about EPR. So the point is, this has been already said in the first paper Schrodinger wrote about entanglement. He said, when two systems of which we know the states by their respective representatives enter into temporary physical interaction, and when after a time separate again, then they can no longer be described in the same way as before by endowing each of them with a representative of its own, representative psi function of its own. I would not call that one, but rather the characteristic trait of quantum mechanics. It is rather discomforting that the theory should allow a system to be steered or piloted into one or the other type of state at the experimenter's mercy, in spite of his having no access to it. This refers to the EPR problem, which I have not described here. How did we end up with a very useful and very accurate theory of which we understand nothing? We do not understand what psi function is. We do not understand why we get the stochastic result. We do not understand why there's an irreducible uncertainty. We do not understand what superposition in the theory means in the real world. We do not understand what happens when you observe. We do not understand how correlations between two particles work. We do not understand the relation between quantum mechanics and classical mechanics. We are not able to counter Einstein's incomplete argument. Instead of getting out of this mess, we have chosen the path of superstition. We now believe that there are telepathic superluminal communication between separated particles that are not interacting physically. We now believe that a particle can be in two positions simultaneously as long as they are tiny. We believe that particle can have 2 or 3 different masses simultaneously. We have just failed to understand quantum mechanics. So in 10 minutes, I want to show you something remarkable. See, there are 2 empirical elements that we should hold as absolutely essential. One is that if we prepare a particle and observe it, we either see it in one path or the other path, and not in 2 paths. In fact, this is completely against all conservation laws. Particle cannot split into different possibilities, because particle in each of these possibilities is with its full mass, full charge, full spin, and so on. Those quantities never split. It's only the possibilities which are splitting. So therefore, matter cannot have wave property. There must be something really wrong about talking about matter having wave property, because matter cannot split into 2 paths or 2 possibilities, because that will violate all fundamental conservation laws. At the same time, we know that there is something in both paths. We know that there is something in both paths because if you take 2 interferometric situations, we can arrange the phases such that the particle definitely appears through this path or that path, because if the phase difference is an integer times 2 pi, it takes one path. If it's the odd integer times pi, then it takes another path. We can arrange in an interferometer these 2 situations with probability 1. However, this can be arranged by introducing phases in each path separately, independently. So therefore, there must be something in both paths. There must be something interacting with optical elements and physical elements in both paths, but it cannot be the particle. So empirically, from experiments, not theory, from experiments, we know that particles should not split into 2, but there is something in both paths which splits. Now, in the current quantum mechanics, what is being done is this. There is some kind of a wave function, psi function, whatever you call it. Then suppose you suppose you are observing a single system, a single particle, you get some result. Let's say the particle is detected at this position. This is a wave function, but the particle is detected at one position. Then immediately you say the old wave function is collapsed into a new wave function. In current quantum mechanics, that's what you do. Then you say a particle can be a superposition of two positions. There's a Gaussian here, another one here. So this is a total wave function of the particle. Then you observe the particle somewhere. The entire thing becomes this wave function in current quantum mechanics. Einstein has already said in 1936 and many times later the following, a warning voice. He said, the psi function does not in any way describe a condition which could be that of a single system. Because he said that is the source of all problems. It relates rather to many systems, to an ensemble of systems in the sense of statistical mechanics. If except for a certain special cases, the psi function furnishes only statistical data concerning measurable magnitudes, because of the very fact that psi function does not in any sense describe the conditions of one single system. Again, the Schrodinger equation determines the time variations which are experienced by the ensemble of systems. So he has been always arguing for this following fact. He was saying Schrodinger equation does not describe a single particle. The wave function or psi function is not corresponding to a single particle. It's an ensemble quantity. However, he also realized he cannot just stop there. He also said, what happens to single system remains, it is true, entirely unclarified by this mode of consideration. This enigmatic happening is entirely eliminated from the representation by the statistical manner of consideration. So he knew that all problems of quantum mechanics will vanish. All foundational problems will vanish if the psi function was an ensemble quantity. Schrodinger equation was not an equation for single particle dynamics. But he also realized then he is left with explaining things like interference, what the single system does. He had an idea what will solve the problems of quantum mechanics, but he didn't have any idea what will also explain the single particle behavior. So what he was saying was the following. Suppose you have a probability distribution, histogram or something, for maybe heights of people, weights of people, something like that. Then you make one observation on a single individual. For example, my weight. So it has some value. So it falls in one of these histograms or somewhere under this probability distribution. So there's a probability distribution, and a single individual in this sample appears with some particular value of the variable. Immediately we don't change the probability distribution, do we? We don't. Probability distribution remains same. An individual is observed with a particular weight. We don't change the probability distribution. We keep the same probability distribution. So we don't do this. If the psi function and the Schrodinger equation correspond to ensembles, we don't do this. There is no collapse of the wave function. Similarly, if there is a wave function which is a double humped wave function here, if you observe one particular example of an individual case, we don't change the probability. We just observed it, but the probability distribution remains exactly the same. That's what Einstein was saying. Let's skip this. So I am also claiming that Schrodinger equation is not the equation for dynamics. It is not the equation for single particle quantum history. We have been completely mistaken for the last 100 years. The Schrodinger equation is for the wave function. So if what I'm saying is true, that the Schrodinger equation is an ensemble equation, then the wave function also should be an ensemble average quantity. It has nothing to do with the matter wave. It has nothing to do with the single particle, and so on. We have to restart from the beginning. But where is the beginning? It's a Schrodinger equation. As I told you, this was the equation which was written for non-relativistic mechanics. Now I'm going to show you something remarkable which changes the whole complexion of quantum mechanics. And with that, we can stop. There is a well-known classical equation for the time evolution of probability densities. It is a classical equation. No, it is very familiar to you. It is called the conservation equation, or equation of continuity of probability density and so on. It says the time evolution of probability density is equal to the divergence of the probability current. This is a conservation equation. For example, if it is a density, real matter density, you would say the density changes by matter flowing out or flowing in from some region. So it's a classical equation. Let's look at this equation. Since rho is a positive quantity, we can also write it as square of some other quantity. Rho is equal to a square, but a can be now plus or minus a. You get the same rho. On the other hand, I can write it in terms of single valued quantity. We have to write it as psi star, where psi is complex. Then the single valued rho is psi star, which is a mathematical transformation where psi is a e to the I phi, where phi is some dummy phase. A is the square root of the probability density. Then the same classical continuity equation is this, because now del rho by del t is this is psi square, psi star. So therefore, when you take the time derivative, you get this. This is a classical continuity equation. Note that the gradient of psi, this is a function of position and time. The gradient of psi is this. Therefore, if you multiply this by psi star, since psi is a exponential I phi, psi star is a exponential minus I phi. So wherever you want to cancel e to the I phi, you can multiply by psi star. So you multiply by that and you get psi star gradient psi is equal to this term plus rho del phi. Now it is interesting. It's interesting because if this del phi is somehow related to velocity, if del phi is velocity v here, then we have the entire term, the rho v also from psi itself. The psi was related to rho, but the psi can be also related to the quantity rho v if we have the del phi as v. So therefore, that's what we do. We equate del phi is equal to v. Then this is the equation we get. This is the same equation. Psi star del psi is equal to a del a I rho v. We take a complex conjugate. We get this. We take complex conjugate of the same equation. You get this. Now we take a difference. You get that. Therefore, this is the equation. This is the same classical continuity equation. Nothing has changed. I have just done a transformation. But the divergence of rho v is the divergence of this quantity, which is just this quantity because other term just cancels in the subtraction. So this is again the classical continuity equation. The classical continuity equation I have just rewritten. That's all I have done. Now you see, this part is this and that part is this. This part, if I take just this part, I get an equation plus another possible term which could have gone cancelled out in the subtraction. I have added that term there. But if this term is not there, I have only this part here. Del psi by del t is equal to I by 2 del square psi. But that is the Schrodinger equation. That is the Schrodinger equation. The Schrodinger equation is just a classical continuity equation. It has nothing to do with the matter wave. It has nothing to do with the dynamics. Dynamics comes into Schrodinger equation only through the velocity, which we wrote here as del phi. It just says that it's a probability density of a dynamical system. That's all. It is not any probability density. It's a probability density of a dynamical system. It's an ensemble equation. And the psi here is the square root, complex square root of the probability density. It's an ensemble quantity. You see the miracle. We have been, and so, but this Schrodinger equation didn't have any h bar and so on, right? But that comes because when I say del phi is equal to V, I don't have such quantities in physics. What I have in physics is del phi, if phi is related to, yes, the action, Hamilton's action, then del phi is P by h bar. And therefore, through that, through the relation between phi and V, or phi and P, I get the rest of the coefficient. For in particular, you notice here this factor 2 here. It has nothing to do with the P square by 2m or dynamical equation like that. It comes because of I have subtracted one quantity from its complex conjugate and divided by 2. So what I'm saying is the classical continuity equation is this, the Schrodinger equation is that, they are the same. It is like we had the geocentric system and it took 1500 years for people to get convinced about the heliocentric system. It was just a coordinate change probably, but conceptually it was such a big leap one had to make. And here we are seeing that the wave function has nothing to do with any physical wave, let alone a matter wave. Its magnitude exactly is square root of probability density. Therefore, Bond's rule is not an extra rule. It's a mathematical consequence of the definition of this. It's an exact relation. We understand why Schrodinger mechanics is a statistical theory, because it's an equation for ensemble. There is no matter wave in Schrodinger mechanics. De Broglie's idea was remarkable, as a history of success of quantum mechanics shows, but it's factually incorrect. Matter itself does not have any wave property. But the dynamics of matter is associated with a genuine wave-like quantity. The question is, what is it? I have written a very detailed paper on explaining what is it. Everybody knows it, but nobody sees it. I can just indicate what it is. I don't want to talk about it. For that, one has to go 200 years back to William Hamilton's paper in 1833, in which he wrote a paper with a very interesting title on a general method of expressing the paths of light and planets together. General method of expressing the paths of light as well as planets. And he said we ought to think epithet least, but rather to adopt the alteration proportional above, and to speak in mechanics and in optics of the law of stationary action. Right? There's a law of stationary action which applies to all mechanics without exception. It can be planets, it can be light, it can be anything else, gravity. But action principle can work only if the action waves are real. The action principle works, there are action for many paths and they cancel each other and chooses one path, the paths of least action or paths of stationary action. How is it possible? Only if the action is manifest in physics, in real nature, as with a wave property. Only then it can cancel between different paths by interference. So action must be something real wave-like quantity in space. It applies everywhere. Therefore, the Hamilton equation cannot be just this, because this doesn't consider the wave property of action. Hamilton mechanics also is incomplete, and it can be completed very easily. That equation can be rewritten. So I don't want to talk about this here. I'm just indicating what is there in that paper, which I referred to earlier. This particular paper in archives, here there are details which it will take time to talk about it. So I don't want to talk about it, but I want to say that it's a Hamilton mechanics, a modified form, which is the true equation for dynamics, not Schrodinger equation. And it explains everything, interference, correlations, everything. So we finally know what entity is superposing in mechanics. It is just the action wave. The proof is simple. Only if the action waves are real, existing in real space, the principle of action could work. Because interference and real waves are essential for that. And we know it works in all mechanics without exception. Just because it is an unobservable, like a field, it is not unreal. Because if it is unreal, principle of least action cannot work. So what I have told you today is a future of quantum mechanics, and indeed of all mechanics. I do not know when it will be recognized as such, but the thick cover of confusion that exists today will be lifted eventually. However, the single fact that it has solved the cardinal problems of collapse, entanglement, and quantum measurement, while explaining the single particle interference, is enough to see its truth value. That it has solved the problems is very clear from what Einstein said about psi function and Schrodinger equation and so on. But again, these things are also explained in that particular paper. So I have cleared the view and revealed the physical reality behind the wave particle dual entity in dynamics, as I promised, and I clarified what is exactly the superposition in quantum mechanics is. It's a superposition of only the action waves, not matter wave, not matter, or not any other quantity. Thank you.
Thanks, Sunny, again for this very, very enlightening talk, and also I think something which needs a lot more retrospection and thinking, and especially there are quite a few younger audience, especially on the YouTube platform, who have been asking lots of questions. I hope this will be something which will be very, very enlightening to them. There are actually quite a few questions. Knowing that it is already 7:20, I'm not sure how many questions we can take today, but let us nevertheless kind of go and try. Let me see. So one question, so this will be in in time. So therefore some of them maybe you had kind of answered. I'll try to see if I can skip that. But is quantum indeterminism related to the uncertainty principle? That's one question. By Vatsal Trivedi.
Is the quantum?
Is quantum indeterminism related to the uncertainty principle?
Yes, of course it is. But now, see, in this talk, I couldn't talk about it. Usually the uncertainty principle is stated as a product of uncertainties in two quantities is greater than or equal to S cross. That is a statement of uncertainty principle. But you see, that's a very convoluted statement according to me. If action and action wave are the quantities which are really superposing, and the reason for all this indeterminism, then the uncertainty principle is much simpler. It should just say the uncertainty in action is greater than or S cross, greater than or equal to S cross. That's all. And since it is applicable to all mechanics, because the action principle is applicable to all mechanics, the uncertainty comes from the action being a wave-like entity, then uncertainty principle is valid, applicable to all mechanics. There is no classical and quantum division. It's the same mechanics all throughout, and the uncertainty is there in every piece of dynamics, including the dynamics of a planet.
Okay, there are quite a few other questions, Uni. So I'll request you to be slightly brief in your answer. If you want to explain Raman emission, for example, we bring virtual states into picture. Is it not so that quantum jumps are not always required?
See, what I have said is unconditional. A single system every time changes its state by a quantum jump. It's unconditional. There is no exception.
Okay. By virtual states, I mean, okay, he was kind of talking. By virtual states, I mean slight continuous change in electronic arrangement around the nuclei due to incoming radiation. So that is the point that he was saying from the when he says virtual states. Now, how do we say that the insect in your example in that slide is not even a superposition state? Can you please explain that point again?
Yes, that's a crucial point. So even if I take 2 more minutes, it's worth it. See, the screen is on. The most general state of a two-state system in quantum mechanics is a superposition of those two states with arbitrary coefficients A and B. The most general state of a system 2 is a similar superposition with another set of coefficients C and D. So this is a state, this is a description of some system which has some state. This is a description of a second system which has some state. The joint states of these two systems together is S1 and S2 written side by side. That's all. If they have their own states. And that is this, the joint state of two systems, two independent systems, which may have interacted and all that. It is, if they have independent state S1 and S2, they are just written side by side with the label 1 and 2. So this is plus plus, plus minus, minus plus, minus minus. This is a two-state systems, two systems, two state, therefore four terms. Now, the entangled state which we talked about, two particles interacted and there are only two possibilities, is a different state. It is this state. This state can never be written as that particular state. That is, this state cannot be factored into S1 and S2 because there are only these two terms. If there was this term or that term, we could have factored it out. It is not. Therefore, this particular state is not plus, it is not minus, and is not a superposition of plus and minus, which is the most general state. It is neither this nor that, nor a superposition of the two. But that is the most general state in quantum mechanics. Quantum mechanics does not have anything more. Therefore, quantum mechanics cannot describe this joint system with states of their own, independent states of system 1 and system 2. And that's a consequence of the this particular way of describing physical states in quantum mechanics. And the same applies for any system. For example, atom and an insect interacted, then there are only two possibilities. Atom in one state, insect live, atom in another state, insect dead. The other two possibilities are not there because of a physical constraint. It can never have atom in state one and insect in dead and so on. Those two states are eliminated by a physical constraint. Then the insect has no state in quantum mechanics because it is not live, it is not dead, it is not in a superposition. Because if it is in a general state, this should have been the state. Atomic state should have been this. The product state would have had all the four terms. It is not there. This has only two terms. So it is not live, it is not dead, it is not a superposition. It has no physical state in quantum mechanics. In real world, whether it has state or not, we don't know. That is what the EPR argument is. There is no one-to-one correspondence between quantum mechanics and real world. Quantum mechanics is incomplete. So it's very serious. And all these conclusions come from the very, very simple fact of superposition, linear superposition in quantum mechanics. That's all what is there in quantum mechanics. And that is a source of all successes of quantum mechanics. That's a source of all problems of quantum mechanics. And as I showed, it is because for the last 100 years, people thought quantum mechanics describes single quantum systems. No, it describes only ensembles of systems. The Schrodinger equation, the wave function, all that corresponds to ensembles. Once we realize that, all problems of quantum mechanics is solved. There's no problems of entanglement or non-locality, nothing. As evident in the simple derivation.
Okay, only we'll move on. One question it says is, in quantum mechanics, do anything smaller than the Planck's length exist having a physical sense?
There is no Planck length. There is only a Planck's constant, Planck action, H cross. Planck length is just a definition. Nobody has seen any Planck length. It's a speculation.
Okay. Again, Vishal, Vatsal Trivedi. If psi represents an ensemble average, even for a single electron, what
does that mean? For a single electron, there's only a single electron, right? No ensemble.
It says, he says that if psi represents an ensemble average even for a single electron, what is it the ensemble of?
Oh, okay.
And what are the individual components?
Yeah, so suppose you take one electron, do an experiment, then repeat the experiment 1,000 times. You get an ensemble, and then you can do an average. And then you get a psi function. But you take one electron, one experiment, there is no psi function. That was a mistake. That was our misunderstanding of the heliocentric system as a geocentric system.
That's correct. There are two more questions. One again from him. Isn't action wave as an observable as psi?
No, that sounds too vague.
Too vague. Isn't it probably? Isn't it action wave as an observable as psi? So it's 1 minute. Let me. Isn't action wave as unobservable as psi? It says. Okay, let us leave to him if he wants to make a bit clarified on that. But just let us take the last question from Purvaja. It is there for you to read on the Zoom chat, but maybe I'll read for you. I have one question. If a particle and its antiparticle annihilate, then how would its wave structure would be? Based on your slide 5, will it be like two opposite waves coming together and cancelling out? In that case, how would the wave structure of the photon emitted would look like? Just to be able to imagine.
See, I want to repeat. When particles annihilate, they don't become waves.
Right.
They become photons. So if photons are particles, they remain as particles. But with the particle and the antiparticle, there will be corresponding action waves. Similarly, with the emitted photons, there will be action waves of the corresponding to the photons. But the particle is just a particle. It has no wave property. Whether it is an electron or a photon, it has no wave property. The wave property is associated with something else, not with the particle. It is associated with the action.
Yeah, I remember you mentioned that.
Any particle, whatever particle you take, for example, a neutrino, it has no wave property. Because as I said, if it had a wave property, and if it was a superposition of two different mass state, then the transition from electron neutrino to muon neutrino should have been a smooth variation with many stages in between. It doesn't happen. It happens by a quantum jump.
Yeah. Yes. Okay. So, sorry. Unni, I think that's all we have questions for you today. Of course, it is already almost 7:40. So I know you had a very nice, wonderful way to kind of bring in this very subtle, very fundamental, but extremely probably important issues that requires a lot of thinking and also maybe a lot of work by everyone, both old and young. But I hope the younger...
the paper has all answers anyway.
That's right. So I was just about to say, I hope they will kind of read through, and of course they can always communicate to you. With that, let me thank on behalf of all the participants, especially the young participants who were very much interested from their questions that they asked on the YouTube. And I'm sure it was very interesting and inspiring talk to them.
I don't see any institute students.
Our own, I'm not sure if they,
students.
If they are there on the YouTube or not, but yes, not on the. I see there were a couple of students. Anil Kumar is still there, and I think there was another couple of students on the Zoom who are the INS students. I think Abik just was there.
The result is that they will learn the same wrong quantum mechanics.
So with that, I would like to thank Unni once again to you, for taking time off yours and then especially preparing this such wonderful lecture, comprehensive lecture for the students in particular. Thank you very much. Thanks. And I just want to, before I close, I just wanted to kind of announce that the next talk on February 8th, that is next Monday, is going to be Professor Rohini Godbole from Indian Institute of Science, Bangalore. She's going to talk, the lecture, the title is Symmetries of Nature and Nature of Symmetries. So again, going to be another equally interesting talk. Please join again. Until then, take care and stay safe. Thank you.